Hello, everybody. Welcome back to a very special episode of How to Write Proofs, or another way to say that is how to survive the rest of this class. We're going to be spending the entire rest of our time together proving things. So, in this first part, we're going to be talking about proving implications. So, things that look like P implies Q. And we saw examples of this last time. One of the things we'll prove later would be something like if f is a differentiable function, then f is a continuous function. Things like this. So this is really important for what we're going to be doing later, and we're going to spend a lot of time talking about the nuts and bolts of how to do it. I think before we start with the nuts and bolts of this, it really helps maybe to talk about a couple of analogies. So, in some ways, writing proofs, it's like making art. In fact, when Stephen Krantz wrote his book on how to be a department chair, he said, being a department chair and being in charge of running a math department is not like you might suspect, like working with a bunch of engineers who are, nose to the grindstone, straightforward, unemotional people. Mathematicians are really much more like artists because they're used to creating things themselves. And keeping in mind that math is a lot like art will help you as running a math department. It also helps you understanding what we're trying to do here when we write proofs. I mean, for example, sometimes people will tell me, oh, I want to be a math major. I really love math because there's always one right answer. Well, I mean, that's true if you're solving some sort of equation, and that's what they mean by that. But when we're writing proofs, as we'll see in the next few minutes, there's more than one right way to write a proof. There's more than one right way to explain something to someone. And it's really important. You realize as you become teachers, different students will understand things differently as you explain it different ways, and different proofs can be done and explained in different ways. The best proofs are the ones that are elegant and beautiful, right? That you look back and you go, "Oh wow, that's really neat," right? Um, Beauty and creativity, though, I mean, they come from being from having done a whole bunch of it and being good at it, right? Learning how to write a proof creatively and in a way that's really cool comes from just having done it a lot. You can't really get this from a YouTube video, okay? But what we can do in a YouTube video, just like you would do in an art class, is study the nuts and bolts stuff, which is what we're going to be spending most of the rest of our time doing. It's like studying the brush strokes or the chisel marks on a statue. It's like seeing, how did the master create this, right? This is what we're going to be doing for the rest of this lecture. The nuts and bolts of how you actually take a brush and put it on canvas. We're going to be talking about how you actually take a pencil and a piece of paper and make a proof. Another good analogy, though, to keep in mind is writing a proof is a lot like playing checkers, right? Especially the kind of proofs we're going to be writing throughout this class. Because first, what you do is you look at what you've got to work with, right? I've got some checkers scattered around on the board. My opponent has some checkers scattered around the board, and think about what you can do, right? And what they might do in return, right? This is sort of like if you want to prove that P implies Q, one of the first strategies we'll have is to think about, okay, I'm assuming that P is true, so what does that tell me? Right? Think about what moves we can make. Think about how you want to put those moves together, and ideally, right, what you'd like to have happen is arrange things so that you go move, 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 jump all over the board, and go king me at the end where you've jumped over, all the checkers they have left. So really beautiful and elegant proofs are ones that you set things up at the beginning, and then the last paragraph or so that you write is just, look, it all just falls out. Right? Now, that is not the way that proofs, you know, when you first start learning how to do them, are going to come together. We will spend some time talking about the fact that you should not think of writing a proof as sitting down with a piece of paper and it all just flows naturally from inside your being. It's really much more about sitting down and doing scratch work. Working out an equation, write down something over here. This doesn't make sense. No, cross that out. And then you play with some equations and then you see how it works. Then you have to rewrite it and write it nicely so that you get this effect of jump, 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 king me, I win. Okay. So when you read proofs in the textbook, what you're actually seeing is the result of of someone having thought for a long time about how to set things up correctly, and then they just jump, jump, jump and win. But when you actually write your own proofs, right, we'll see as we go through this that you're going to have to spend some time figuring it out on scratch paper. And I don't want you turning that in. I don't want to see your scratch paper stuff. What I want to see, unless I ask for it, and I may do that once or twice just to make sure you're actually doing it that way. What I really want to see is that you've worked it out ahead of time and thought of the right way to set things up, then rewrite it clearly and precisely so that it looks cool, right? All right. There are in the stuff we're going to be working on three major proof techniques that we want to talk about. So if we want to prove an implication like P implies Q, okay, if you look back through the tautologies that we saw in our last videos, there's lots of different ways you can put P's and Q's and nots and ands and get things that are equivalent to P implies Q. And that leads us to three different ways you might try to prove something. For example, you might do a direct proof or an indirect proof or a proof by contradiction. And we're going to slowly work through all three of these different proof techniques so that you understand A, what they all are and how to use them, and B, maybe more importantly, when later I tell you, you know, prove this in the homework, and here's a hint, do a proof by contradiction, you'll know what it is that I'm talking about. So, first up are direct proofs. So this is the most straightforward kind of way you prove something. We want to prove that P implies Q, right? If P is true, then Q is true. So the easiest way to do that is just to assume that P is true and show that Q has to be true. Okay? So, okay, what does that really mean? That really means this. Number one, you go and you write down anything you can think of that P implies. So if we assume that P is true, then what does that tell us? What do I know about that? Right? For example, in the example I said before, if we want to prove that if a function is differentiable, then it's continuous. So we start out by assuming we have a function which is differentiable. Okay, great. Now what do I know about that? Right? We have to go back to the definitions, what it means for a function to be differentiable. And then maybe look around and see, have we proven anything already about differentiable functions? Because we can use those. Those are things like theorems, or in the books they may be called propositions or lemmas, or things that are things we've already proven. We know that. We can use any of those, right? So that gives us our tools we can use to start working, right, from the P direction, right? Thinking about what happens when we assume that P is true. On the other hand, you might also start thinking about what happens that would tell me Q, right? So in other words, in the example I said a second ago, if f is differentiable, then it's continuous. So what does it mean for a function to be continuous? What would tell me that it was continuous? Okay, well, it has a definition. Then there's some other theorems that tell me that something's continuous. All I have to do then is pick one of those, right? And if I can prove that, then that gets me to Q, the thing I'm trying to prove. And then the hard work, of course, is we spend all our time trying to connect the dots between parts 1 and parts 2, right? So this is the real nuts and bolts of how you do a direct proof. And now we definitely need an example. So we're not doing number theory in this class. If you've taken a class in writing proofs before, you may have seen proofs like this where we try to use something that you all know really well and go from there. We're not going to, eventually we'll be writing proofs that use calculus ideas. So this is not going to be a proof about algebra, even though I'm going to talk about n being even and n squared being even and things like that. Even and odd are simple enough ideas that I think everybody will get those without having to learn a bunch of new math. So first theorem we want to prove. If n is a positive integer and it's even, then n squared has to be even. Now this is pretty obvious when you think about it, right? If a number's even, then when you square it, it's still even. And you kind of think of a few examples, like what happens if I take 6 and square it, I get 36, that's still okay. But then I'll kind of make sense, right? So how do we start the proof? If we're going to do a direct proof, we want to assume that n is even. Okay, now what? Right? What does that mean? What we really need is a definition, something we can work with. So we go back to definition. So here's a definition of what it means to be even. I mean, you might say something like, it means you can factor a 2 out of it. Okay, what does that really mean? So here's a very precise, mathematically correct definition of what it means to be even. So positive integer n is even if there's another positive integer k so that n is equal to 2k. In other words, I could factor out a 2 and that leaves me a k. That's what that really says. But this, having this k here, right, and having a way of actually very clearly and precisely saying what I mean by factoring something out, right? Because if you're not careful about this, you can make this mistake. Is 3 even? Well, no. Right? But could I factor a 2 out of it? Well, yeah, right? But what I would get when I factor a 2 out of 3 is 3 halves, which isn't an integer. This is why we were very careful here to say that a positive integer is even if there's another positive integer, right? So that n is equal to 2k. Okay. All right. So here we go. Let's suppose that n is a nice positive even integer. What we have to do is prove somehow that n squared is going to be even. Okay, so that means that, well, I've got to find a way to factor a 2 out of the n squared, right? So that's part of my end goal is I need to start with what we know about n and work our way over to get that n squared equals 2 times something. So how do we do this? Well, our definition says there's some positive integer k so that n is equal to 2k. That's our definition. That's, remember, we're trying to prove p implies q. Like we said, p is that we have a positive integer n that's even. Q is that n squared is even. We started with p. What that tells us is that our n is equal to 2k for some positive integer k. Now, what would our q mean? It means that n squared is even, which means that n squared is equal to 2 times something. It won't be a k, of course, but it'll be some positive integer. So how do I do that? Well, this is where the work comes in, right? Let's start writing out what this means. I know something about n, so what does it tell me about n squared? Well, all I can really do is take what I know about n and square it. If n is equal to 2k, n squared is 2k squared. Okay. So I don't know where to go with this, right? So we sit here and we scratch our head and we stare at the paper, we look at the wall, we stare out the window, and eventually we think, well, 2k, all in parentheses, squared. If I just do some algebra, I mean, that's like 4k squared. And what am I trying to get? I'm trying to get it to look like 2 times a number. Oh, wait, I could make that 4 be 2 times 2. So I could write that as 2 times another number, 2k squared. Well, that's perfect because 2k squared is a positive integer. K was a positive integer, so k squared is a positive integer. When you multiply by 2, it's still a positive integer. If you don't remember what an integer is, of course, integers are whole numbers, right? That's why we weren't allowed to have 3 halves before as an integer. 2k squared is a positive integer, so that means I have taken n squared. I've written it as 2 times a positive integer, so n squared has to be even, so we're good. Right? Now, if this was confusing, rewind the video or rewatch it again. Make sure that you follow how things work. It's not always clear why I did things as I did until you get to the end, and you go, oh, that's how it works. And what I've written up here is the nice final actual proof. My scratch work for something like this would look something like, n equals 2k, and then I'd have somewhere a 2k squared where I'm trying to play with it. I'll just write down these equations and see what happened. And finally, when I got down and realized that n squared was 2 times parentheses 2k squared, I go, oh, that's it. Then I start over writing this up nicely. Okay, one quick word about the n's and the k's and stuff that we've been using. So you notice that we started that last proof by saying, suppose that we have a positive even integer, we're going to call it n. So in doing that, we're assuming that p is true, that n is a positive even integer. That was what we were doing. But we also used a variable there, right? See, we let n be an arbitrary positive even integer. Arbitrary is the right word here. We didn't assume that there was anything special about n, and we left it as a variable. So if we do that, then when we're done, what we've proven has to be true for all positive even integers. Okay, this is how we're going to and why we do things with variables. We pick an n, we leave it as a variable. We don't assume that there's anything special about it, like that it's 15, or we don't assume in the back of our mind that n is bigger than 5 or anything like that. We don't assume anything special about n other than what we said, which is that it's a positive even integer. And that's all we're going to use about it, is that it's a positive even integer. Okay? So we can use the definition of what it means to be a positive even integer. We can use other theorems we know about it being a positive even integer, but we don't use anything else. And we leave it as a variable so that it's completely arbitrary. Right? Then when we're done, we've proven a for all statement, just like we learned about in the video on quantifiers. So this would not be a valid proof of the theorem we were trying to prove, that if n is a positive even integer, then n squared is a positive even integer. Because if we just said that, suppose n is 6, then n squared would be 36. Oh, that's even. So every positive even integer squared is even. Yeah, that's not right. Right? I've proven that 6 squared is even. That's all I've done. This is not a real proof of the theorem we're trying to prove. It's a proof that 6 squared is even. Okay, fine. But it's not a proof that every even number squared is even. Because what we've really done here is misunderstood quantifiers. We've shown that there exists an n so that when you square it you get something even. Not that for every even integer n, when you square it you get something even. That's one reason why we spent so long talking about quantifiers. Okay, well, you also noticed that I started out my proof, and I've used several words to separate the equations and things, like suppose and so forth. It's important maybe to take a second and talk about words, because we will probably not want to constantly say suppose this, suppose that. So here's a list of some synonyms you might use. Suppose that n is an even integer. Let n be an even integer. Choose an even integer n. Fix an even integer n. Take an arbitrary even integer. Call it n. Okay? All those mean exactly the same thing. All of those are logically equivalent. There's nothing different about them, but it just sounds better. Okay, one of the things that we'll get better at as we go through this class of writing proofs is, you know, if you use the same words over English words over and over and over again, it's really boring, and it sounds like you're just learning how to write proofs, which of course for now you are. But as we get better at this, you want to get better at writing proofs that sound good when you read them. Especially, take that fix for a second. Later on in the class, we will um, start a lot of proofs with fix an epsilon greater than 0. Okay? And that's just traditionally the way that people always say that. They use fix a particular epsilon, which is bigger than 0. Um, and that's okay, because that's typically how people always say that when they start those kind of proofs. We'll see when we get there. You'll remember, I hope, when we get there, oh, he's fixing something. It doesn't mean fix it like, it was broken. It means, reach out and fix one, like nail it to the wall. That's the epsilon I'm starting with. But things just sound better if occasionally you suppose something. Then maybe in the next homework problem you choose something. And maybe a homework problem later you take an arbitrary one. Right? Also, you notice that I said then a couple of times. This happened, then this, then this, then this, then this. That also gets boring really, really fast also. So other words that mean the same as then that help you write proofs that just sound better. Then, maybe thus, therefore, hence, so, now, blah, 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 next, comma, something or other. I especially like consequently and as a consequence and as a result. That sounds really fancy. You can say it follows that n squared equals whatever the equations are, or notice that n squared equals 2k squared equals 4 times parentheses 2k squared parentheses, or observe. Those are all words that mean the same thing, and there's no magic to using any of them. In fact, it's perfectly okay to just say then every time. There's nothing wrong with that. But again, it sounds like you don't know how to write very well, right? And we want you to learn to write really well. So you might consider grabbing an index card or two and writing some of these synonyms for then on your index card, maybe some of the synonyms for suppose on an index card. And as you go through writing your proofs, then occasionally just grab one of these and throw in there instead of just then. I mean, at least maybe try then, thus, hence, therefore, you know, um, then, thus, therefore, then, thus, therefore. Isn't something? Um, the truth is, that's often how I write things. You just sort of, circulate among some of these different words. But it does make things sound better when we do that. Okay, next kind of proof. Indirect proofs let us do something really cool by not trying to do a direct proof, assuming that P is true and proving that Q is true, but instead we try to prove the contrapositive. And sometimes that's a lot easier. Sometimes it's awful and we don't want to do it that way. But sometimes this is exactly what we want to do because the way that, well, what Q and P means, right, makes it such that proving the contrapositive is much easier. What this means is we assume that Q is false, we assume not Q, and we have to prove that P is false. We prove not P. So remember that P implies Q and its contrapositive, not Q implies not P, are exactly equivalent. So proving one is exactly the same as proving the other one. So what we're really saying here is instead of trying to prove P implies Q directly, let's prove the contrapositive directly. In other words, assume not Q and prove not P. And we do the same kind of steps we did before. Let's write down everything we know about not Q, right? Then figure out what we know about not P and try to connect the two. So here's an example of the same theorem but with an indirect proof. So if we have a positive integer n that's even, then n squared is even. So we know this is true. We just proved it with a direct proof. But an indirect proof would go something like this. Let's suppose not Q. Remember, we're going to assume not Q and have to prove not P. So it means we have to assume that n squared is not even, and we have to prove that n is not even. Again, so what does that mean for n squared to not be even? Well, again, we do the same kind of steps we did with a direct proof. We say we're assuming that n squared is not even. So what does that mean? Well, let's go back to the definition. The definition said an integer is even if you can factor a 2 out, right, and have a positive integer left over. In other words, if n is equal to 2k for some k. Notice this is another quantifier statement. There exists a positive integer k, right? So for n squared to not be even, the negation of that would mean there does not exist a positive integer k, so that n squared is 2k. Okay, so what do we do with this, right? How do I get this whole thing about n squared not I mean about n not being even, right? This, what am I going to do with this? Well, so I think back through what I know about numbers, and one thing that I remember is the fundamental theorem of arithmetic. Now, super important. You have to know your definitions and theorems. We'll say this over and over and over throughout the class. And one reason why we have homework due the way we do is that we want to emphasize you have to start doing homework by learning all the important definitions and theorems. Otherwise, you don't have any idea where to go next. Right? But if you know the fundamental theorem of arithmetic, which just says a positive integer can be factored into a bunch of prime numbers, then that's something I could use, right? Because if n squared is not even, right? Okay, well, n squared, I've got to be able to factor it into a bunch of prime numbers. So what does that tell me? Well, those prime numbers don't include 2. That's right. That's what it means if n squared is not even. I can't factor it and have 2's that show up in there. Okay? So I can use that, right? Since n squared is not even, 2 is not one of its factors. Right? How do I know that? Well, remember, if it was, I'd factor it out, and everything that's left over could be my k. So I'd factor out the one of those 2's, and I'd be left with a whole bunch of other prime numbers. Multiply those together and call that k. Ding, where n squared would be even, so that's why it doesn't work. Okay, now here's where it gets interesting. This is where maybe this indirect proof is a little harder than the direct proof we did earlier, but it does bring up something that will be important in a proof we're going to see later. So this is, and I'll remind you when we get to that point that we talked about it here. N and n squared have to have the same numbers as their prime factors, right? If you think about that, think about a number like 21. Now this is not part of the proof. This is just an example, right? But examples are important, right? Think about a number like 21. It factors into 3 and 7. What does 21 squared factor into? Well, 3 and 7 and 3 and 7. In other words, the factors of n squared are the same numbers as the factors of n, but you just list them twice. I'd get, if at 21 squared, its factors would be 3 and 3 and 7 and 7. In other words, 3 squared and 7 squared. So that's pretty obvious, right? That's just algebra. So if n squared is not even, that means that n squared can't have 2 as a prime factor, then n can't have 2 as a prime factor. Okay? Because it's the same numbers that are the factors of n and n squared. Just in n squared, they've all been squared. Right? So we can't factor a 2 out of the n, so we can't write n equals 2k for some positive integer k. Probably should have said some positive integer k. So n can't be even. So that means that if we're thinking about this in terms of p's and q's, we assumed not q, and we ended up proving not p. N cannot be even. Now again, this may have seemed a little bit more complicated, and of course it was a little here. But there will definitely be times where this is the easier way to go in proving a theorem. So understanding the structure, the brush strokes, right, how this was created and put together is really important. Instead of proving P implies Q, we've just proven not Q implies not P. Okay, lastly, we could do a proof by contradiction. So to do this, instead of trying to prove P implies Q directly, right, what we try to prove is that not, parentheses, P implies Q, parentheses, is false. Okay, that doesn't sound like that helps, right? But here's the key. What's the negation of an implication? The negation of P implies Q is P and not Q. Oh, that's cool. Okay, so now what we're trying to prove is that P and not Q is false. So what we do is we assume that P is true, we assume that Q is false, so we're assuming P and not Q, and then try to find a contradiction. In other words, we try to prove that P and not Q is false. Okay, so why does that help? Well, actually, this helps a lot because notice we're getting to assume two things. We're assuming that P is true and we're assuming that Q is false. That gives us two things to work with at the beginning. So when I sit down with my scratch paper and I start writing out stuff, I don't just have a definition that says that like n is even, right? What I've got is also that n squared is not even, right? I've got two things I'm assuming is true, so I got two places to start to work trying to put things together to make a proof out of it. That can be really cool. And then I don't have to actually prove that something's true at the end. I just have to find a contradiction, something that's obviously false. Okay? So how might this work? Well, here's our theorem again. If we have a positive integer n which is even, then n squared has to be even. So I'm going to assume P and not Q. In other words, assume that n is even and n squared is not even. And again, so what does that mean? That means that n is equal to 2k for some k, but n squared is not equal to 2 times some positive integer. Okay, so that means that there is a positive integer k so that n is equal to 2k. That's what it means for n to be even. But n squared is not even. That means there does not exist a positive integer m so that n squared is 2m. Or remember we've talked about negations of quantifiers. If I don't want to say there does not exist a positive integer m, another way to say that is for every positive integer m, n squared does not equal 2m. It's the same thing. Now, you notice I suddenly used an m here, and the definition had a k. Where did that come from? Well, it's really important. I already used k. Once you start writing a proof and you start using a letter, then you've told me what that letter is, and you can't go back and change it into something else. There's no taking back what you've already said. So since we've already said that k is the number that you multiply by 2 to get n, right, we know what it is. It's n over 2. K is a particular number. When I need another number, right, to use for n squared to show that it's not even, then I've got to use another variable. I'll call it M, or you can use any letter you want to. Maybe L might have been a better letter to use here, because K, L, M. But I don't like using L if I can help it, because sometimes L's look like ones. So that's why I skipped over L and went to M. But you call it any letter you want to. It's your proof. You do whatever letter you want to. It was my proof, so I picked an M. The important thing is I do want to use different letters here. And sometimes that confuses people, because they'll go back and they look at the definition and they'll say, the definition says this number is even if it equals to 2k. So n squared not being even means it's not equal to 2k. That's true, but I've already used k, right? And that k in the definition was just a dummy, right? It was just saying that there is some integer that works. So the name isn't really important. It's what it does that's important. That's why I have to use two different names here, a k and an m. Make sense? Okay. So how do we prove this? Well, we're assuming that there is a positive integer k, so that n is 2k. There's no positive integer m, so that n squared is 2m. Okay, but then what happens? We start doing our calculations now. If we're assuming that n was 2k, then of course that meant that n squared has to be 2k squared. And if you play around with that, that means that's 4 times k squared, which means it's 2 times 2k squared. So if I rewrite with the parentheses like I have there, I get 2 times parentheses 2k squared. Okay, and of course that was the same calculation we did when we were doing a direct proof. It's not shocking, because this is proving the same theorem, but now we state it a little differently, because we're assuming, right, that n is equal to 2k. We're also assuming that n squared is not 2m for any m, right? For all, right? So another, again, this is the negation of an existential statement. So another way of saying that is, for all m, n squared does not equal 2m. Okay? But if we call 2k squared m, right? And you might go, oh, wait a minute, wait a minute. You say we had to use a number? Well, remember, I'm talking about for all m. So if I said, look, here's an m, 2k squared. If m were equal to 2k squared, then m is a positive integer, and n squared is 2 times that particular m, 2 times k squared. So there's my contradiction. In other words, I'm assuming that for all positive integers m, n squared is not 2m. But look, I just made an m that was 2k squared, right? I just made an m so that n squared was 2m. That's a contradiction. So we assumed that n was even, that n squared was not even, and we got a contradiction, right? We were assuming that for all m, n squared is not 2m, and we've just found that n squared was equal to 2m. So that's a contradiction. The original theorem has to be true, because our assumption that the original theorem was false is false. Two negatives make a positive. It's essentially how proofs by contradiction work.